Math 265A, Cuesta College. I'm Joe Vasta, and today we're going to cover section 3.3, Rules of Differentiation, or what I like to call shortcuts. This is when life is going to get a lot easier when it comes to derivatives. So I'm assuming right now we don't know any of the shortcuts, and we're going to develop a list of shortcuts in this section, which is a good thing. Now all the shortcuts are going to come from the definition of the derivative, which includes the difference quotient. So if I'm assuming we don't know any shortcuts, and the function is 3, why, I'm going to take the derivative, find the derivative. So dq is f of x plus h minus f of x all over h. Okay, well, this is kind of a funny function because whatever you plug into it, there's no x's on the right hand side, so whatever you plug into it, the output is 3. So if you go f of trash can, that equals 3. So f of this junk, f of x plus h, is going to be 3. We have a minus sign, and f of x, which is 3. This is all over h. Look what I have here. I have 0 over h, which is 0. So the dq is 0. The derivative is the limit of dq as h approaches 0. Well, it's just 0. So we found the derivative of the function f of x equals 3. Now imagine if it said f of x equals 5 or f of x equals 7. The same thing would have happened, and the derivative would have been 0. In terms of a picture of what just happened, well, what does the picture of our function look like? The picture of our function looks like this. So here's the y-axis, the x-axis. Here's x, here's y. Y equals 3. Looks like this. It's a horizontal line. What is the slope of each point on that line? Well, you draw the tangent line, it is that line itself. The slope is 0. So the derivative, f prime of x, is 0 for any horizontal line. Any horizontal line would just be any constant. So now what we have is we have the constant rule. And so I'm going to write out the constant rule. We don't need to prove it or anything. And the constant rule looks like this. So this is number 1 of our shortcuts. So not to be confused with problem number 1. We'll have, I think, about 6 rules. And the constant rule goes like this. You take the derivative. So that's the other notation for the derivative. That means I'm gonna put that in front of the function I want to take the derivative of. The derivative of the function c, in our case it was 3, is 0. And this is called the constant rule. Okay, so that is our first rule of derivatives. It's a shortcut because, like, if you in your homework you have another one that says f of x equals 17, you don't have to do dq anymore. Now you can just say it's 0. Now, of course, on the test, if they ask if they ask you to find the derivative using the definition or using the difference quotient, you have to show the work on that. But for the most part, from 3.3 beyond, you can use the shortcut. Let's go to our next problem. Our next problem is, actually, I'm not going to number this problem because it's just something maybe we should know how to do. How can you go x plus y to the fifth? Well, some of you might guess you can go x to the fifth plus y to the fifth, which is actually incorrect. X plus y to the fifth, you would have to do this. There's 5 of them. And so you'd have to multiply the first 2 together with a FOIL, and then multiply and multiply and multiply. It's going to take a long time to do this. So there is something called the Binomial Theorem, which is a shortcut. And I'm going to just go through it kind of quickly. It involves something called Pascal's triangle. Pascal's triangle has a 1 up top, and then there's 1s there. So this makes a little triangle. I'm going to make the triangle a little bigger by adding another row. And the number that you get right here is from adding the 2 numbers above it. So 1 plus 1 is 2. So look at this. We can make the triangle bigger. And then the number that goes right here is you add the numbers above it. 1 plus 2 is 3. 2 plus 1 is 3. So the next row would be 1. And then we add. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And then we put a 1 there. So Pascal's triangle has symmetry. If you divide it right in half, what you see on the left is the same thing as what you see on the right. This row that I just wrote is row 4. We know that because 4 is the second entry. So row 3, row 2, row 1. This is row 0. Let's go ahead and write out row 5. 1, 5, 10, 10, 5, 1. And once again, I'm getting these numbers by adding the 2 numbers above. So 10 is gotten by going 6 plus 4. Okay, so there's a 10. So how do I do this? These give me the coefficients that I'm going to get here. So I'm going to go ahead and write out row 5 sort of in a vertical fashion. 1, 5, 10, 10, 5, 1. So basically I'm doing the binomial theorem. I could use summation notation and make it more algebraic, but I'm not going to. I take that first term within the binomial and I take it to the full power, x to the fifth. Now as I run down the line, it's going to decrease in power. So x to the fourth, x to the third, x squared, x to the first, and then this one right here, which I'll do in red because you don't really need to write it, is x to the 0. So this guy is completely alive and then dies. Now this guy over here is going to be completely dead on the first term, which is y to the 0. And then he's going to come to life. Y to the 1, y squared, y cubed, y to the fourth, y to the fifth. Now what I'm going to do is I actually have 6 terms. So this thing right here, the first term is 1 times x to the fifth times y to the 0. Y to the 0 is 1. So this is x to the fifth. The next one is 5x to the fourth, y. The next one is 10x cubed, y squared. (10x squared y cubed). 5xy to the fourth. And then the last one is y to the fifth. The binomial theorem is a shortcut for taking binomials, that's 2 terms, to a power. Now, is there a trinomial theorem? you don't have to worry about that, but there is. If there was a trinomial x plus y plus z to the fifth, well, there is an extension of this to a higher dimension called Pascal's tetrahedron. But we don't want to go there today. We want to get back to the calculus. We are going to do a derivation, and I'm going to do probably like 4 derivations in this lecture, and the derivations are going to be on PowerPoint. So I'll be switching back and forth between me writing on a piece of paper and the derivations which are on PowerPoint. Also know that when you are getting ready for the test, I'm not going to have you do the derivations that you see on the PowerPoints. Those are there just for your entertainment. So I have the function f of x equals x to the fifth. And what I want to do with this is I want to take the derivative. Because there's going to be lots of times when we want to take the derivative of x to a power. Is there a shortcut that we can develop? Well, I think there is. Let's go ahead and figure out dq. dq, well, it's this part right here. It's without the limit. It's f of x plus h minus f of x all over h. And I'm going to go ahead and apply that to x to the fifth. My dq looks like that. X plus h to the fifth minus x to the fifth all over h. So now what I'm going to do is I'm going to go ahead and I'm going to multiply out that x plus h to the fifth. It is a binomial to a power, and we talked about this. We can use Pascal's triangle. And so the red numbers you see there are the numbers from Pascal's triangle, row 5, 1, 5, 10, 10, 5, 1. It's very similar to what we did on the piece of paper, except we have an h instead of a y. Okay, now I notice that this expression has an x to the fifth and a negative x to the fifth. So what I'm going to do is I'm just going to get rid of those. Okay, now I have that. The next thing I'm going to do, for some strange reason, there are 1, 2, 3, 4, 5. There's 5 terms on the top of that fraction. I'm going to look at the last 4 terms and factor out an h squared on this term, that term, and that term. And I'll factor out that h squared to the right-hand side. Okay, that's what I did, just doing some algebra. Now this polynomial, you know, it has some h's in it and has some x's in there. I'm going to now classify that polynomial, this may be offensive to some people, as a junk polynomial. So I did that. Okay, now what I'm going to do, and I'm not going to show all the intermediate step, I'm going to factor an h out of the top and cancel it with the h on the bottom. So my dq is going to end up being 5x to the fourth plus junk polynomial times h. Now why did I call it a junk polynomial is because I'm going to be taking the limit of dq as h approaches 0, so that's going to go away. And that's why I called it a junk polynomial. And so look at my result. The derivative is 5x to the fourth. So we could ask ourselves, do we see a pattern up here? Well, this is x to the fifth. And then down here, I mean, the 5, there's a 5 like in front of that, whereas the 5 was the exponent. And now the exponent's not 5 anymore, but it's 4. Now, sometimes one example doesn't let us in on the pattern, and maybe it does. Maybe you're like, wait a minute, maybe that exponent jumps down in front, and then that power or the exponent is replaced by 1 less. So we think that could be our shortcut, and now we're going to prove this for any exponent n if n is a positive integer. So n is a positive integer, and we have x to the n. Okay, so this is going to be very theoretical for some of you. I'm going to go ahead and go to the nth row of Pascal's triangle. Oh, well, before I do that, let's write dq. And then this is from the nth row of Pascal's triangle. Now, you can sort of verify this on your own if you want. I'm not going to write out the whole polynomial, but I'm going to write out the first part, x to the n. And then this is, since I'm on the nth row, it's going to be n, x to the n minus 1, h. And then the rest I don't care about, and I'm just going to say that's multiplied by h squared, and I'm going to call that junk. And then I have minus x to the n, which you see up there. So the x to the n and the minus x to the n go away, and you have that. I can factor an h out of the top. There's two terms now. We can think of that as two terms. And then it cancels with the h on the bottom. I end up getting this down here. And what am I doing for the derivative? This is dq. The derivative is the limit as h goes to 0. I end up getting f prime equals n, which is that exponent there. It jumped in front and it got replaced with the exponent that is 1 less. So this will also work for non-negative integers, meaning it will also work if n is 0. And we'll see an example of that on the paper. So we'll go back to the paper now. Here's the rule that we just proved, the power rule. Take the derivative of x to the n. It equals n times x to the n minus 1. And I'm changing it here. I'm saying that n is a non-negative integer. So I'm including 0 in that as well. So here's notation for a derivative. And this is an operator. You can think of this as sort of a derivative gun. So here's a little creature. And you're going to zap it with the derivative gun. So there's the derivative gun. And so that's just another way of saying we're going to take the derivative. See here, you might feel more comfortable because the next step I'm going to say f prime, but I actually have to write out f prime equals something. On this, I can just say let's take the derivative. Zap that with the derivative gun. So the power rule says this 3 jumps in front. So that puts a 3 right there. Okay, and that's what I'm doing. I'm looking at the power rule, and then I have x, and then we have, replace that with 1 less than 3, so x squared. Now, because of this shortcut, wasn't it a lot nicer to do this problem than to actually do difference quotient with x to the 3rd and go through all that work? Yeah, and that's why we like the shortcuts. Okay, so let's now take the derivative. The directions are take the derivative, and we've already done one of those problems. So this one says f of x equals x to the 50th. So maybe you want to pause the video and see if you can write out the correct derivative. Now, of course, when we start this problem, we can't just say equals. We're going to say f prime of x equals. So you can pause the video and see if you can write out the right answer. Okay, the power rule says this 50 jumps in front. Then you have x, and then you replace it with 1 less to the 49th power. And so there is the answer. You could just box the 50x to the 49th if you'd like. So we have it. Now, let's point out a few things. I'm going to just get you ready for future sections, so we might as well get used to it now. Sometimes n is a negative integer. I'll just abbreviate that. And if n is a negative integer, this power rule will still work. The proof of that will be in 3.4. Here's another deal. Sometimes n can be just any real number. So n can be pi or 1/2, any real number. And guess what? The power rule will still work. And that can be proved in 3.9. Now the proofs are not things, and when you see the PowerPoint, don't worry oh, I've got to know how to do that. No, that's just showing you why this rule works. So you don't need the difference quotient anymore and the definition of the derivative for these kinds of problems. But instead of just saying, I hate the definition of the derivative, you can say that. But when you're doing these shortcuts, they came from that definition. Let's go ahead and do this one. Y equals 1 over x squared. Well, 1 over x squared is really x to the negative 2. So look what I have. I have a negative integer. So even though the proof comes in 3.4, we should know how to do this. So the derivative, I'm not going to say this equals the next thing. I'm going to say, well, this is y prime equals. Okay, so y prime is the derivative. So that derivative, we're going to go x. This negative 2, you're going to subtract 1. That's what it says. So it's going to be minus 3. And the negative 2 actually jumps in front. Okay, now we want to simplify our answer, meaning we don't want negative exponents. So to simplify our answer, let's just rewrite this. This is y prime equals. There's always a fraction on this. You can always put things over 1, and we can cross the line, change the sign. Change the sign of the exponent, not this sign. So my final answer is going to be negative 2 over x cubed. And so there's the derivative. So the power rule, once you get used to it, you'll never forget it. I mean, you might not become a math major, but you could, if you live to be in your 90s and you're on your deathbed, that power rule will still be there. You're like, no, it won't. Oh, it will for a lot of you. So that's something that's probably going to stick if you've had a calculus class. G of W. Oh, we switched it to W's. Oh, this is tricky. It's not that tricky. This is square root of W. Now, do you remember what a square root is? A square root is really a power. It's the 1/2 power. So let's go ahead and zap this thing with a derivative gun. We have G prime of W equals, okay, power rule. So this 1/2 is going to jump out front. You're going to have W, and then you're going to go 1/2 minus 1. Well, what is 1/2 minus 1? It is negative 1/2. Okay, so the same thing as in the last problem. We do not want a negative exponent in our answer. So our derivative will equal 1 over 2 times W to the 1/2. Cross the line, change the sign. So this is an acceptable answer. Now, if you want to show off your math nerdiness, there's an answer that's going to be, it's just going to look a lot cooler. We have 2 times the square root of W. And this is going to make you look a lot cooler when you go to a math nerd party. So this actually does look nicer. You know, you don't have to write a little tiny exponent, and both are acceptable. So that happens to be the power rule, which we'll use throughout the rest of this section. We're going to go back to PowerPoint to prove our next shortcut. We have 2 shortcuts already, the constant rule and the power rule. The next one will be constant multiple rule. Okay, so now what we're going to do is we're going to derive something called the constant multiple rule, which means if you've got a function and it's multiplied by a constant, usually just a real number, what will happen? And so what we're going to do is we're going to plug this into the derivative. Okay, so when I do that, c times f of x. So f of x plus h is going to be c times f of x plus h. And then we have minus c times f of x, because c f of x is now our function. This is all over h. Okay, and all this is a proof. So some of you might just want to skip ahead to when I start doing examples again. This is almost done, by the way. So on the top, I have a c on both terms. I can factor it out. And in fact, that c does not have an h. It's not an h, so I can pull that c outside the limit. So that's what I did. See, there he is right there. Pulled him outside the limit. And now this part right here looks just like the definition of the derivative of f. That's what it is. So it just says when you go to take the derivative of a constant times a function, it really is the constant times the derivative of the function. Now, if this still looks kind of weird to you, let's go do an example on the piece of paper. So let's get back to some examples. In the PowerPoint, we just proved the constant multiple rule, which is this. Here's your derivative gun. Taking the derivative of a constant times a function, it's the constant times the derivative of the function. So let's see what we do here. The rules are take the derivative. We have a constant times a function that we know how to take the derivative of, which is x to the fifth. So basically, what we do when we get something like that is we are going to write the 3 there, and then take the derivative of x to the fifth. So I'm going to do a step that a lot of people don't write, and I probably won't write this in the future. And we can go like that. So it's like this 3 can just sneak on the other side of the gun. Come on, who wants to be zapped by the derivative gun anyway? So he sneaks on the other side. That's what the constant multiple rule is. So now let's take the derivative of x to the fifth. Well, I think we've done that before. So this is multiplied by. The 5 comes down. We have x to the fourth. So our final answer happens to be 15 x to the fourth. Okay. Now we don't really need to do this problem because we know what the answer is. The derivative of 2 is 0 because of the constant rule. But I'm going to show you this problem in a new light. So like if you were just doing this on the test, you would say, oh look, the derivative of the function is 0. And say, okay, there, we've figured that out. I'm going to go ahead and do this in a different color just to show you some insight on this. So here's f of x. This is 2. Now, look, what you really have next to that is an x to the 0. So watch this. When you go to take the derivative, we have the constant multiple rule where we could just say, oh, well, the 2 just is going to be there, and then we'll take the derivative of x to the 0. We've never done anything like this. The 0 jumps down. X to the, we go 0 minus 1, so this is negative 1. Now, I know some of you are like, go across the line, change the sign, but it doesn't really matter because this is all getting multiplied by 0. So this just kind of proves that all the rules gel together. You're not going to get any contradictions if you think about it in a different way. Hopefully you'll never do this. You'll have a constant and you'll just remember that the derivative is 0. So now it is time to go back to the PowerPoint to do another derivation. So what I'm going to do now is I'm going to derive something called the sum rule, where you're taking the derivative of a sum. So how's that going to work out? Well, this thing that's in the parentheses, that's going to be my function. So, I mean, you could label that function h of x if you want, but I'm not going to do that. I'm going to go ahead and throw that function into the definition of the derivative. And so look, this first part right here is the x plus h part, and then this is just subtracting the function. This is all over h. Okay, so what I'm going to do is distribute that negative sign right here and distribute it to those guys. And take the parentheses off the first two things in the numerator. So we have that right there. Now what I'm going to do is I'm going to go ahead and group the f's together on the top. And then I'm going to group the g's together, secondly. So look at do that. We're just rearranging terms. And then after I group them, I'll break that into two fractions. And the limit of a sum is the sum of the limits. So that's what I'm going to do next. So I have that. Now, what does this look like? This right here looks like the derivative of f. Do you see that? And then this guy right here looks like the derivative of g. That's what it is. And we have that right there, f prime plus g prime. The derivative of a sum is the sum of the derivatives. That is what the sum rule says. Let's go take a look at the difference rule, which will be very similar. So there's the derivative of a difference. We can go back to the definition, but we don't need to now. I'll just do this a different way. So if you're like, you want to be a math major, I mean, this is for you. If you're just like, I'm just taking this class, I don't know why I'm taking this class, then skip ahead to when I start doing problem number 8. So the derivative of that difference, we can write minus g as plus a negative g. So now I have two functions, f of x and negative g of x, and there's the sum. And because of the sum rule, we can say the derivative of the sum is the sum of the derivatives. So we just proved that rule. And we have the constant multiple rule where there's a -1 in front of that. So we can factor that -1 out in front of that derivative gun there. So that's by the constant multiple rule. And then the first part right there where it says d dx f of x, another way of writing that is f prime, and then over here is g prime, and there's a minus in between. And so we've just proved the difference rule, which says the derivative of a difference is the difference of the derivatives. See, this is the derivative of the difference is the difference of the derivatives. So now we're going to go back to me writing on a piece of paper. We'll do a few examples, and then we'll hit one more derivation on PowerPoint in this lecture. So let's go ahead and do problem number 8. We have the sum rule and the difference rule. We just derived those. And what do I have here? I have a function that is a difference. And so basically what it means is when I take the derivative, I can take the derivative of 2x to the 4th, which is what? The 4 jumps down in front. So this is going to be 2 times 4x to the, and we replace the 4 with a 3. And because of the difference rule, I can go minus and then take the derivative of x cubed. The 3 jumps down in front and is replaced by 1 less, which is a 2. Oh, by the way, next time I take the derivative of something like 2x to the 4th, this is that rule that we were saying, this the constant multiple rule. Next time I'm just going to go ahead and multiply the 4 by the 2 and just write it as 8. But I didn't do that this time. So what do we have? This is going to be, I'm doing it right now, 8x cubed minus 3x squared. There it is. So imagine, like, if you didn't have shortcuts, plugging this into the definition of the derivative that has the difference quotient and all that jazz, we take this whole piece of paper, maybe more, to get this result. So shortcuts, they're really nice. Why don't you pause the video and see if you can find the derivative of g of x. Okay. Before I take out my derivative gun and start zapping each of these guys, I see this square root of x. We've encountered a square root already. We're going to change that to the 1/2 power. So I'm rewriting g. I'm not taking the derivative. 1/2 x squared minus 3x plus 8 plus 2x to the 1/2. Okay, take out your derivative gun and zap each of these guys. And that we're doing sum rule and difference rule, and we're just taking the derivative of each of these and adding them together, or we'll keep that minus there. So here is g prime. The derivative of this guy right here, the 2 jumps out front, so it's going to be multiplied by that 1/2, and that's just going to be a 1. So this is just going to be x, and then we have to the 1 power. Now, of course, we better not write our answer like that. That's like putting a 1 in front of an x and saying 1x. So we have x to the 1. We're going to rewrite our answer. What is the derivative of negative 3x? Well, there is a 1 up there. And you'll get used to this as you do more problems in your homework. The 1 jumps down and gets multiplied by the 3. So we have minus 3x to the... you're going to go 1 minus 1. Okay, that's a 0. And that takes care of that one. So like next time, maybe when you see a negative 3x, you'll say, oh, the derivative is negative 3. Y equals, because that x to the 0 is going to be 1. Okay, so that's going to turn into negative 3. You could also think of this as the graph of y equals negative 3x is a line that has a slope of negative 3. And so there's many ways of thinking of this. What's the derivative of this constant 8? Well, it's 0. And the derivative of 2x to the 1/2 power? Well, the 1/2 is going to jump in front, going to multiply by that 2, so you're going to have just 2 times 1/2, which is 1. And then this is going to be 1/2 minus 1. 1/2 minus 1 is negative 1/2. Okay, so let's write out our derivative. This is x minus 3. Okay, so remember the x to the 0 is 1. I'm not going to write that. And then I'm going to cross the line, change the sign, and write it as 1 over x to the 1/2. So there's the derivative. Now, I did skip some steps. I didn't write the 1/2 times 2 in front of here. And I didn't write the 2 times 1/2 in front of this one. So, sue me on that one. I don't know what I'm going to do. So, x minus 3. And then this is plus 1 over root x. This is for all you math nerds out there. Look at this. We're just partying with the square root of x. So there it is. That's how you do derivatives. And I just couldn't imagine doing this using the definition. I couldn't imagine doing all that algebra. I mean, it would just be a mess. And then taking a limit as h goes to the 0, you would get exactly one of these guys. Okay, in your homework you may from time to time get a problem that has like more than one letter. Now this says f of t equals this expression. So when you see something like this, we're going to assume that a and b are constants. They may tell you that, and they may not. But if it's the case and it says f of t equals something that has other letters, we'll assume those are constants. What does that really mean? It means just like assume the a is a 6 and the b is a 7. How would you do that problem? Could you do that problem? And the answer is, I think we can. F prime of t is, okay, the 3 jumps out and gets multiplied by the a. So what is 3 times a? That's 3a. So I'm going to write 3a t, and then we're going to say one less than that is 2. So 3a t squared. And plus b is a constant. What is the derivative of a constant? 0. So my final answer is 3a t squared, and that is the derivative. So we have 5 of our shortcuts. The next shortcut that we are going to experience is something that has e in it, okay? The constant e. So we are going to see how we do with that. So we're going to go back to the PowerPoint one last time. So let's go ahead and start off with something kind of weird. The limit of e to the h minus 1 over h as h approaches 0. Now, if you go ahead and you throw h into this, h equals 0, you get 1 minus 1 on the top, so 0 on the top and 0 on the bottom. So what to do? What we're going to do is we're going to do this the old-fashioned way, where we have that number e, which is a constant, and we'll talk about that a little bit later on this derivation. So you should have a button, an e button on the calculator. And so what I'm going to do is I'm going to let h equal 0.1, because it's pretty close to 0. 0.1 is pretty close to 0, and let's see what we get. We get h is 0.1. This expression, e to the h minus 1 over h, becomes 1.05171. Well, I'm going to get closer to 0, so maybe h could equal 0.01. So look at this number changes a little. This number is 1.00502. I'm going to let h equal 0.001. Interesting. And I'll let h equal 0.0001. And so what is happening to this expression? It looks like it's getting closer and closer to 1. So, not that we should always do things numerically, but I'm going to do that this time. The limit of that expression equals 1. Well, if you look at a lot of calculus books and other places, they will actually define the number e using that limit. So I'll put it in a box down here. The definition of the number e. E is the number such that the limit of e to the h minus 1 all over h, as h approaches 0, equals 1. It's kind of a weird way to define a constant. Like when you define pi, you can say the circumference over the diameter, and boom, there's something physical. But this, it just seems a little bit more mysterious. Okay, so what is e? E is 2.7. So it looks like it's a repeating fraction if you just looked at the first 10 digits maybe. 1828, 1828. So if you cut it off right there, you would think it would be like 1828, 1828, 1828. But nope, it kind of deceives us and then goes 4590, etc. And it seems random. It's not really random. It's what makes e what it is. But it's like pi, where it's an irrational number. There's actually ways you can remember e if you wanted to remember it. I could say, well, how many letters are in the word to? Well, now that's kind of confusing, but I'm using to. So there's 2 letters in to. And how many letters are in the word impress? Let's see, I-M-P-R-E-S-S. There's 7 letters in the word impress. A only has 1 letter. Fraction. So I'm going to say a statement that can get us to 13 digits of this. To impress a fraction of students, I remember to numerate this short statement. And that takes us all the way to the 9. Okay, so there it is. What are we doing with this? Well, what we're doing is we want to use this to get another derivative shortcut. Okay, so there's the definition of e. There's the definition of the derivative. We want to take the derivative of e to the x. So I'm going to plug that in to this definition here. Well, so the first part, it's going to say limit as h approaches 0, and then when I go f of x plus h, it's going to be e to the x plus h. So that's what it looks like. Okay, now this e to the x plus h, I'm going to use properties of exponents to sort of split it up so it says e to the x times e to the h. We do that all the time when we go x squared times x cubed gives me x to the 5th. You went 2 plus 3, so going back this way, you can see we do that all the time pretty much. Okay, now I'm going to factor out an e to the x on the top, and I do. Now that e to the x does not have an h in it, and it's just e to the x multiplied by another expression, so I'm going to let that come out in front of the limit. I can do that because there's no h on that. So now I have this. Now look at that top definition of the number e. It says limit as h approaches 0 of that expression. That's exactly what we have here. That happens to be the number 1. So the derivative of e to the x is e to the x. And if we're looking at this d dx, we're looking at the derivative as a derivative gun that zaps the functions. Look what happens when you zap e to the x. You get what? Itself. So it's its own slope function, and that's why people like e to the x. It's the Superman of all functions, because when you hit it with the derivative gun, it just keeps walking towards you, and then you hit it again with the derivative gun, it's still e to the x. That's pretty scary for some people, especially if you're trying to destroy e to the x. Maybe you're Lex Luthor of the math world and you do not like e to the x. Okay, our last slide is going to summarize the 6 rules that we had, and I'll include it in the PDFs. So there they are: constant rule, power rule, constant multiple rule, sum rule, difference rule, and the derivative of e to the x. So that will end all the derivations that we do on PowerPoint for this lecture. Okay, we're back to the paper, and here's that statement I said. To impress a fraction of students, I remember to numerate this short statement, and that gives you about 13 numbers there. You guys also might appreciate this one. May I have a small container of orange juice and 3 pancakes? Look at that one. That helps you memorize pi. There's another one, but I didn't want to write it down because it was a little longer. How I want a drink, alcoholic of course, after the heavy lectures involving quantum mechanics. So that one goes a little further. In any case, the whole idea of looking at the last rule was to show you that the derivative of e to the x is e to the x. And it's the only function where it's its own derivative. So let's take a look at some problems here. Problem number 11. Problem number 11 says f of x equals 3e to the x. So look, f prime of x, is the constant multiple rule mixed with the last rule. It's 3e to the x. So there's the derivative. And we can box the whole thing, or we could just box 3e to the x. Okay, let's go ahead and do this one right here. The derivative of g is g prime. So I'll write out a few more steps on this one. We have the 5 halves. The 3 jumps down in front. It becomes a 2. And then we have minus 4e to the x. And then this one has a 1 for the exponent. So we have minus 1x to the 0. So the derivative of that happens to be 15 halves x squared minus 4e to the x minus 1, because x to the 0 is 1. Here's your derivative. That's what we learn in 3.3. There's a few other problems that we should do to make it so you're ready for your homework. Let's go ahead and do problem number 13. Can you take the derivative of a piecewise defined function? And so that does look scary. You know, like, oh, whoa, how are we going to do that? But it's not as bad as you might think it is. So one thing to see that if you put 2 on the bottom one, you end up getting you get 12, and you put 2 in this top one here, you end up getting 7, 8, 9, 10, you get 11. So there is a jump discontinuity. Oh wait, yeah. So it's a jump discontinuity. It jumps, which means it's not differentiable at the point 2, at the x value 2. Well, that's all right. In our answer, we're not going to include 2 in our answer. So we'll be careful. Right here it says less than or equal to 2, so we're not going to include that. Let's take the derivative, and what you're going to do is what some of you might guess that you would do. The derivative of this piecewise defined function is a piecewise defined function, and you just take the derivative of each piece. So the derivative of 2x minus 7 is 2 plus 0. Okay. And the derivative of the bottom, 3x squared, is going to be 6x. Okay, now the top part's going to be if x, we keep the same thing, except we do have to be careful. We have to say x is less than 2. We don't put equal to because this function is not, so I'll just put it right here, not differentiable at x equals 2. Okay, so that's why we don't include it there. And then down here we're going to say x is greater than 2. So that's the way you take the derivative of a piecewise defined function, or sometimes these guys are called branch functions. Okay, so look what we have here. We have x minus 1 times x plus 1. So you might ask the question, is there a product rule? Is there a product rule? We have a sum rule and a difference rule. The sum rule says the derivative of a sum is the sum of the derivatives. Well, is the derivative of the product of the derivatives? And the answer is no. The product rule is actually a little bit more complicated, and we'll deal with that in the next section. So you don't have to write that red part down. So the only way we can deal with this product is to multiply it out. First, outside, inside, last. This is going to give me an x squared. It's a difference of squares, so x squared minus 1. This is the only way we know how to do this problem when they're asking us for the derivative. So f prime is actually, we just take the derivative of this polynomial term by term. 2x minus 0. I'll write that down, but we really don't want to put that in our answer. So the derivative is 2x. And that takes care of problem number 14. Problem number 15. Look what I have. I have a quotient. That means it's like a fraction. You have stuff on the top, stuff on the bottom. Is there a quotient rule? Well, there is a quotient rule, and that's going to be more complicated than you might think. The derivative of a quotient is not the quotient of the derivative, so I wish it were that easy. This is going to be in the next section. And I know some of you are like, wow, now I have something to look forward to. Yeah, you do. Okay, but how can I do this? Well, I'm going to go ahead and split the fraction. Because there's one term on the bottom, you can split the fraction. Now, if there were two terms on the bottom and one term on the top, you could not split the fraction. And then you would have to know the quotient rule. But right now, let's, we gave one that's like this. And in your homework, if you get something like this, hopefully you're not too perplexed, especially if you've looked at the lecture. So splitting the fraction looks like that. If you're kind of confused about splitting the fraction, we could always split a fraction. I mean, look at this. If we had like 3 minus 1 over 4, well, we know that that's 2/4, which is 1/2, but we can go 3/4 minus 1/4. And so that's called splitting the fraction. Let me put a cloud around there. Okay, so there it is. Okay, let's simplify this. So you have to know how to simplify exponents. X to the 7th over x to the 3rd is x to the 4th. So this is 1/2 x to the 4th. This one right here is going to be minus 1/2. You have x to the 4th, x to the 3rd, x. Okay, so now take out your derivative gun and aim. So I have 1/2, the 4 jumps down, x to the third minus 1/2, and maybe we could just keep it that way, but I'll write out the step here. 1 jumps down, x to the 0. So x to the 0 is actually 1. The derivative then, if you simplify things, is 2x cubed minus 1/2. And that finishes problem number 15. Let's go ahead and do some other ones. You're going to see some weird problems like the following problems in your homework. Problem number 16 and 17 use this graph here. Okay, well actually it's a graph of two functions. Here's f, which is a line. Here's g, which is another line. And then they have this. It says if capital H, which is not on the graph, but capital H equals f plus g, then find h prime 1. Okay, so h prime 1. Well, what we're using here is really the sum rule. If you want to take, if h actually equals that, and you're trying to take the derivative of h, it's going to be the derivative of these guys, and you add those derivatives together. So this is the sum rule. So h prime of 1 is going to equal f prime of 1 plus g prime of 1. Okay, that's just because we're using the sum rule and h equals f plus g. We could have written for a step h prime x equals f prime x plus g prime x. But we didn't write that. This is where we'll go to. And what do we have here? We have, how am I going to find f prime of 1? Well, f prime of 1 and g prime of 1, well, here's 1. But let's face it, anything that is on the graph of f, any point on the graph of f, if you draw the tangent line, it's going to have the slope of the line that you see. So the slope of the brown line, line f, is what? Rise over run. You're a little bug, you rise up 1 over -1, because you're going in the negative direction, so the slope of that brown line is -1. The slope of g, the purple line, let's see if I can find my purple pen, is rise over run, and let's see, you rise up 2, and you run to the positive direction 1, so 2 over 1, which is 2, so this has slope of 2. I just lost the pen cap. Okay, so f prime of 1, it could have said f prime of 7. It's the same thing because it's all on the line. So f prime of 1 is -1 plus g prime of 1. Well, anything on g would have a slope of 2, so this is going to be 2. So this equals that. And then, of course, you add those together and you end up getting 1 for the answer. Number 17 is similar, a little bit more complicated because there's some numbers there. We'll see if you can do number 17 on your own by pausing the video. Okay, so k prime of 3 is what they're asking for. Well, that's the derivative of this, which is a difference in some constant multiples. So really what it's going to be, it's going to be 5 g prime of 3 minus 3 f prime of 3. Now, if you make it all the way to a linear algebra, you'll find out that the reason you can do this is because you're working with something called a linear transformation. Of course, now I'm talking in the clouds, so I'll get out of the clouds and continue to do this one here. 5 g prime of 3. Well, here's 3, and right here, what is the slope right there? Well, the slope is still going to be a 2. we have minus 3 times f prime of 3. F prime of 3 is right here, but it still has slope negative 1. So it looks like I have 10 plus 3, which is 13. So 13 is the answer to problem 17. Okay, we're going to continue. Do a few other kinds of problems that look like the homework problems. And we're starting the numbering back at 1 again because, you know, once you get up to like 17, that seems like a lot. And this is a different kind of problem. So the next few problems, all the way to the end of this lecture, will involve this function, x cubed minus 3x squared plus 1. So this is a polynomial. And it asks, find all points on f at which the tangent line is horizontal. So remember, horizontal looks like this. And tangent line is horizontal, which means that would be the slope is 0. So find all points on f at which the tangent line has slope 0. And then this one's going to say tangent line has slope 9. So let's go ahead and do this one first. Well, if they're talking about the slope of the tangent line, what we absolutely need on this problem is the derivative. So what is the derivative of that polynomial? And this may be a good opportunity for you to pause the video and just like on a piece of scratch paper, see if you can actually crank out problem number 1. Well, what I'm going to do is I'm going to calculate the derivative, which is 3x squared. We have minus 6x. And then this one right here is the derivative of a constant is 0. I'm going to go ahead and box that. That's not my final answer, but I put it in green because I'm sure we're going to be using it down here as well. So how do you find this? This is the slope function. Okay, so we plug numbers in there, and then like you plug like a 1 in there, and it ends up giving us the slope at the x value of 1. So that slope would be like negative 3, but we're not looking for negative 3. We're trying to find when the slope is horizontal. So what you want to do with this is you want to set this equal to 0, and that will tell you the x values that will have slope 0, or where the tangent line is horizontal. So it kind of boils down to, can you solve this quadratic equation? And I know some of you are like, hey, do the quadratic formula. That's killing an ant with a cannon. It'll get the job done, but it will make a big mess. I think when it's like this, I'm going to factor something out, like maybe a 3 and an x. So I have 3x, and then this is x minus 2. This equals 0. And what do I do with each of these factors? Well, okay, so I'm going to move up here because I didn't give myself enough room, did I? 3x equals 0. Set each factor equal to 0. X minus 2 equals 0. So I'm going to actually get two x values. X equals 0. X equals 2. Now, what are they asking for? They are asking for find all the points. Okay, so our points are going to be ordered pairs. 0, comma something. And then the other one's going to be 2, comma something. Now, how do I get the y values? The y values are gotten by plugging the x values in there, and these should give you some nice y values. I know I'm writing over my work there, and that upsets the perfectionist. Oh well, what are you going to do? So if I plug 0 into the function f of 0, I end up getting 1. And I plug 2 into that. Okay, this is a little more complicated. I'll talk you through this. 8 minus, so this is 2 squared, 4 times 3, so 8 minus 12. So I'm at negative 4 plus 1, which is negative 3. So we have found all the points on f at which the tangent line is horizontal. Now, let's do some visual satisfaction with this. We're done with this. So in the homework, you're done and you move on. But because I'm a math nerd, I'm going to show you the graph of this and show you that these points are on the graph of this and they have a tangent line that's horizontal. So 0, 1, there's the graph of f. 0, 1, look at this. If you draw its tangent line, it is horizontal. Look at this. It has slope of 0. What was the other point? The other point was 2, negative 3. I draw that point. Look at this. Here's the tangent line. You know, when the tangent line is 0, this is interesting. That would indicate something about the graph. It would indicate where there is the top of the hill or the bottom of a valley. I am foreshadowing. You thought that you can only foreshadow in an English class, but we're doing that in a math class, so that's going to be a big topic that comes up later on. And I'm not a perfectionist. Well, maybe I am. I don't know if I am. But I want that line to be a little bit thicker because some of you might not be able to see it, and there it is. Those are, and it's kind of smearing there. Okay, so those are the 2 points on the graph of f, a polynomial who have horizontal tangent lines. Well, that's going to help us in the business world. It's going to help us in the engineering world. It's going to be very valuable in the real world where we try to find our maximums and our minimums. Okay, so that is more foreshadowing. Let's go ahead and do problem number 2. Problem number 2 says find all points on f at which the tangent line has slope 9. So we have our derivative here. And we want the x values that when you plug them in here, a 9 comes out. Well, that's a pretty steep slope, so we'll look on the graph after we get this, if it's on the graph. Maybe it's out of range. I'm going to set this not equal to 0, but I'm going to set it equal to 9. So look what I have. Let me just go ahead and write this equation here. 3x squared minus 6x equals 9. I have a quadratic equation. To solve a quadratic equation, what I'm going to do is put everything on one side. So this is 3x squared minus 6x minus 9 equals 0. Before you take out the quadratic formula, I mean, there's some people I know, they take out the quadratic formula all the time. Anytime they want to solve a quadratic equation, they're like, oh, I got the quadratic formula. Just hold off on that. I mean, I know these people, they take the quadratic formula out on a date. They're shopping. They're like, hey, look at my quadratic formula. So try to stay away from those people. We might need the quadratic formula, but I think what we should always try to do is see if it factors. I'm going to divide each term. I'm dividing both sides of the equation by 3, but I'm dividing each term by 3. And so what does it give me? It gives me x squared minus 2x minus 3 equals 0. Are there factors of 3 that subtract and give you 2? Yeah, 3 and 1. 3 times 1 is 3, but their difference is 2. So that means we don't need the quadratic formula. There's a time and a place for that, but now the quadratic formula will still give you the correct answer. It'll just take a long time to do that. There's the x's, factors of 3. We said 1 and 3. And now we adjust the sign so it gives us a negative 2. So look, negative 3 plus 1. What do you do with each of these factors? The same thing we did over here. We set them each equal to 0. And it looks like we have 2 x values. The first x value is negative 1, and the second x value is 3. Find the points. Okay? So to find the points, you actually want to write physical points here. And you're going to get these y coordinates. I won't put arrows going all the way down here, but I'll put it in orange so you'll know. You're going to put those up top. So if I put -1 up top, look what I have. I have -1 times -1 times -1. Or we could have said -1 quantity cubed. So that's -1. And then when -1 is squared there, that gives you a +1, but it's multiplied by a -3. So -1 minus 3. Now we're at -4. -4 plus 1, -3. 3 gets plugged into this. 3 cubed is 27 minus 3 times 3 squared. That's like 3 times 3 times 3. That's 27. 27 minus 27 plus 1. So here's the answer. It says, find all points on the graph of f at which the tangent line has slope 9. There they are. Let's do some visual satisfaction on this. Okay, so for this, the point -1, 3. I'm not going to draw the 9. But that looks like it has a pretty steep slope. And actually, because of the calculus and algebra that we did, that slope is 9. And the other place that has slope 9 would be 3, 1, which is right here. That point. Like that. It looks like that has slope 9 as well. I'm not going to draw the tangent line, just because maybe I'm too lazy, or maybe in the last video I tried to draw one with grids and it was slightly off. So we'll just do that. Now when you do your homework, you don't have to do this graph part. You just have to find the points that they ask for. Let's go ahead and do another problem that involves this polynomial. Okay. So here it is. Find an equation of the line tangent to f at a equals 1. Okay, so in the book they'll say a equals 1, and that's really the x value. So you're trying to find an equation of the line tangent. So you're trying to find the tangent line. So what do we need? Well, first thing we need is the derivative, and we already did the derivative in the last problem. 3x squared minus 6x. So this right here is an x value. Let's see if we can do this. To find a line, you need a slope. And I think we could get a point as well. So this is what I'm going to do. I'm going to plug 1 into the original function and see what I get. And then we're going to see what that means. So I plug 1 in there and I get 1 minus 3 plus 1. So it looks like I'm going to get the point -1. Now what does this really mean? Well, when I plugged 1 in there, and I was plugging numbers into that function and the other problems, that gives me the y coordinate. So the point 1, -1 is on that graph. Now when I put the x value of 1 into the derivative, it doesn't give me the y coordinate, it actually gives me the slope. And so that's what I'm going to do. When I put 1 in here, it's pretty simple to see that it's going to be 3 minus 6. So it looks like the slope is -3. This right here is the slope. Or, we could say m is -3. Now before we move on, if this was the position function of a bug, 1 would be the time, 1 second. -1 would be where the bug is at 1 second, at -1 on the number line. And this point right here, -3, would be the instantaneous velocity at time 1. So time, position, instantaneous velocity. If you care, do you really have to care on this problem? No. Let's go ahead and finish this problem. We're just finding the line that has this slope and this point. We've done this in this class already. Y equals mx plus b. We've already mentioned there's 4 letters there. 2 of them are variables, x and y, so they can change. And 2 of them are constants. We already know one of the constants. It's -3. Okay, so we got that from that. We're going to plug the point in there. So this is one instance of x and y. So y is -1. This equals -3 times x, which is 1 plus b. So -1 equals -3 plus b. What does b equal? Well, looks like b is going to equal 2. So now, I mean, look, we were almost done when we had this right here. So now we know what b is, and we have y equals -3x plus 2. Find an equation of the line tangent to f at the x value, and they call it a, x value 1, and there it is. It is y equals -3x plus 2. Now for some visual satisfaction. So we have the point 1, -1. There's the graph. There's the point 1, -1. And this time actually on this picture, and I'm doing this on a computer algebra system, I went ahead and graphed y equals -3x plus 2. You can see that it has a y-intercept of 2 and it has a slope of -3. And look, it looks like a nice tangent line to that point. We found that. And so there it is. One more problem and then we'll be done with section 3.3. Okay, it's going to involve the same polynomial. So what is it asking me to do in problem number 4? Find the first 4 derivatives. Okay, so now this is the concept that there can be higher derivatives. And let's do that. And then we'll talk about some notation as well. F prime is, we've already done this, so this is 3x squared minus 6x. Okay. F. So here's the notation for second derivative. Double prime. F double prime of x is. So what we do is we zap this guy with the derivative gun. And so it ends up being what? 6x minus 6. Okay. The first 4 derivatives. So then the third derivative, f triple prime of x. So we zap this with the derivative gun. The derivative of 6x is 6 and the derivative of a constant is 0. Now, we're going to go ahead and zap this guy with the derivative gun. Once we get past 3, putting like little tick marks up there, it's hard on the eyes, especially if, you know, it's late at night and you're doing your math. So the convention is beyond 3 derivatives, the 4th derivative and higher, the notation is you put a 4 within parentheses. Okay, so we already know, oh, well, that can't be an exponent because what's up with the parentheses? That's a derivative. That's the 4th derivative of x. How weird is this? And what is the 4th derivative when you zap 6 with the derivative gun? It is 0. We're done with the problem, but you guys all might want to stay around till the end of the video because there's some explaining I have to do with notation. Okay? So before we get going, let's just talk about the application on this. The original function, you can think of it as a position function. Okay? And the position function maybe is measured in feet from the origin. You take the derivative So let me just put a capital D there. You take the derivative of position, and we know that we get the instantaneous velocity, which would be this first derivative here. Now, think about this. Okay, so the position is like feet. Oh, by the way, we're done with the problem, but okay, this is foreshadowing here. Velocity is feet per second. What happens when you hit the velocity with the derivative gun? Well, if going from here to here, you divide it by seconds, you're going to divide by seconds again, and you're going to get feet per second squared, which is acceleration. So this is feet per second squared. And usually that's where the discussion ends. That was funny. I'll do one more. Okay, so the acceleration is right there on the second derivative. The last one that I'm going to do is you take the derivative of the acceleration. So the acceleration is how fast your velocity is changing. How fast the acceleration is changing, most people don't care about it. And people will call them jerks. But that's what it is. The derivative of the acceleration is the jerk, feet per second cubed. I'm not going to put feet per second cubed. You don't even have to know that. Okay. The next thing I want to talk about, notation. This guy right here could have been a y instead of an f of x. In which, if it was, you would have said this is y prime, y double prime, y triple prime, and don't say y quadruple prime or I'm going to slap you. I can't. Okay, but it's going to be this one right here. We don't say quadruple prime, we just say the fourth derivative. Okay, here's the part where some of you might not like. Remember the Leibniz notation for the derivative? So this derivative right here, it's dy dx. So a lot of people don't like that when they first learn calculus. Okay, so I hope you're sitting down. I hope you're not walking downtown with your cell phone, watching this video, crossing the street, because this could actually kill you. The second derivative notation, d2y over dx2. So when I first saw that, I was pissed off. Like, what is happening? Okay, we'll continue. I'll give you some rationale behind that. Okay, look at this. Third derivative, d3y over dy, dx. That's an x there, okay? Hopefully that's obvious. Dx cubed. And then the fourth derivative is d to the fourth y over dx to the fourth. So why would they do this to us? Why would they do this to us? Okay, well, look at this. There's an innocent y. Okay, it's that guy. And you sneak up with the derivative gun, d dx of y. And what does that give you? That gives you dy over dx, which might remind you of rise over run. But if you wanted to take two derivatives of this, so let me go ahead and put another derivative gun in front of that. So it says, like, I'm going to take the derivative, I'm going to zap it with the gun, and then whatever this is, that's like that right there. I'm going to zap it with the gun again. Okay, so that's how people would write it. This is the operator, and sometimes there is a time and place for operator notation. And in higher math, you know, mathematicians would go, oh yeah, I do like the d dx better. Well, what do you think happened? Well, people want to shorten this up. So y is really on the top. Even though I kind of write it there in the middle of that fraction bar, it's really on the top. So what people started doing, let's just take the second derivative, and you could do it with the third derivative by putting another gun in right there, but this will explain it. So people start going like this. Well, this is really going to be d, d, y on the top, and dx, dx on the bottom. Okay, so that's, let's put a line here. That's what that becomes. Okay, so it's just like I put two guns there, and then I'm just like, hey, let's put everything on the top and put those guys on the bottom. Well, then they go, hey, well, you know what, dd, why don't we, especially if we had like the seventh derivative, we don't want to write d, 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 d. So they would go, well, why don't we just use an exponent? So d squared y. And then you know what, we'll just use an exponent on the bottom. dx quantity squared. But then what happened over time? The same thing that happened with the square root sign. Remember the square root sign, and then you have a cube root? Well, at first, I'm sure some people may have put a 2 there, but what happened is the square root is the most common thing that people got lazy and said, you know what, if we don't have a number there, it's a square root, because it's the most common one. And then cube root, you still have to put the 3 there. Well, that's what happened here. People got lazy, and they didn't want to write something. What did they not want to write? They didn't want to write the parentheses on the bottom. And they thought, oh, we're in such high math, we all understand each other. But it really confuses people when they're first learning it, and there is your notation right there. That is the rationale of why there's a 2 there and a 2 there. It's because they lined up the derivative guns and used some exponents. It was good to up here, and then they got lazy and said, let's not write the parentheses each time. And so that notation comes up. You still might not like it, even though now maybe you understand the motivation of why that's there. Everybody's favorite everybody's motivation, I want to say that word again, I guess. Their favorite notation really is usually the prime, double prime, triple prime, whether it's f or it's y. But you gotta know this if you're going to take more technical classes, because you may end up in a technical class where all they're using is the Leibniz notation. That's this notation right here. Well, that pretty much covers 3.3. I hope that you'll be able to do your homework without freaking out. I mean, it's a bunch of shortcuts. But do your homework nevertheless. Have a good day, and I'll see you in the next video.